make a couple of announcements, and then we'll get down to business. So just what we'll do today is we'll finish handout 6, and then I'll start handout 7, and that's available in the handout folder week 5. So download that if you haven't got that yet. And to me, that's one of the most interesting things about Babylonian mathematics, what we're going to talk about in handout number 7. So on Thursday, I'll give you your next group project, and I owe you grades on that. I know I will get those. I'll get those to you soon. That's my mistake. And then there'll be soon, and probably give it out on Thursday, but a problem set. I have it written. I just want to make sure that it works. You'll have at least a week to work on that. Certainly across the weekend. So that'll come out soon too. And then we'll finish. Also on Thursday, we'll have the introduction to the Greek mathematics. I'll give you your projects. We'll spend some time on those. Talk a little bit about Greek mathematics. And I will have the introductory video, and I should have that out to you either tonight or sometime tomorrow. Again, just to sort of introduce Greek mathematics. So that's it for me in terms of announcements and things. Questions anybody has? Okay. And in terms of time for the semester, we're doing pretty good. I was looking at my schedule last year, and the Babylonians always seem to take a little bit longer than I expect, but we're about where we were last time I taught the course. Okay. So I don't see any questions or hear any questions, so we'll go forward. Where we were is last week we were looking at multiplication, and then kind of what the idea was. I'm not going to go through it again. I think people got that if we wanted to multiply, I'll just take this as an example. We use this multiples of 130 table, and we're just using 130 just because the table exists. There were most likely lots of tables for other numbers. And so we would break one. What I would do here is notice there's 2 places. So I'm just going to get rid of the decimal places, or the sexagesimal places. I'm going to multiply these numbers. And we broke them up into 130 because we had the table for that, plus 1. And this one, 20, because that's an easy multiple. We have 130 times 20 right here. So we'll take that 24, and then we'll also do 4, which we have over here, 4 times 130. So we basically divided it into, into a binomial and a trinomial, and had to multiply it out and use the distributive property. And then we did our work, and at the very end we adjusted for the places. Since we had 2 sexagesimal places here, whatever answer I got here, I moved the semicolon in 2 spots. And so that was the basic algorithm that we used. And what I want to do today is talk about the reciprocal tables. And that's this second table right here on handout number 6. And the first question is, that I have here is just find some reciprocals. So we just started to talk about this a little bit, but I'm going to look at this. I'm going to pin this so I can see it better to my screen. And so you hopefully have it in front of you. So let me get a little bit closer. So I'm going to look at this table here, and then I'm going to look at this first entry just for the sake of it. Okay. And the way you read this is you had, these are all factors of 60, 1, 0. So if I look at this entry right here, I get 2 times 30 is equal to 60. Okay. Now, if I play games with the sexagesimal point, I can make this equal to 1, and I can do that by adding a semicolon here. 2 times 1/2 is 1, or over here. So I can take these multiples of 1, 0, and I can, just by adjusting with the sexagesimal place, I can make these equaling 1. And what that does is it gives me reciprocals. So if I look at this, 2 times semicolon 30 is 1. That means that 1/2 is equal to 30. Or alternatively, over here, I get 1/30 is equal to semicolon 2. So 2 over 60. Sorry, let me get this so you can see it better. So what this really has encoded in it are reciprocals. And, well, what good is a reciprocal? So let's go and let me just try to convince you of the worth of that. We'll come back to this. Let's say that I want to divide something, and I'll do base 10, 705 by 40. If you get out your calculator, one way to get this answer is to do this. That's the same thing. I mean, it's obviously, if you use your calculator, you're just going to do the division. But one way that we can think of this is 1 over 40 times 705. And so the Babylonians could do the same thing. Like, let's say to multiply 1/2 times, they probably wouldn't use it for this. I'm doing this just for examples. Let's say to multiply 1/2 times that number. I'm sorry. Let's say to divide this number by 2, which you wouldn't really need a lot of work to do. I can think of this as 1/2 times 1 comma 57, 1 semicolon 57. We saw before that 1/2 was equal to 0.30, 0 semicolon 30. So I could always perform the multiplication. And again, if they're using tables to do this work, being able to multiply a number by its reciprocal makes, that way they can use that multiplication algorithm for division. Sorry, a little bit dark today. I'm going to see if I can adjust the contrast. Okay, so does that make sense? That to do this simple one, which again, you could do this probably in your head or by hand. If you wanted to just as a proof of concept, we can think of it as 1/2 times 157. Then I go to this table and I say, oh, the reciprocal of 1/2 is 30. And again, that's the rationale right there. And I can just multiply it. And so you can see that if it were bigger numbers, then it might make sense, you know, if you're dividing by 52 or something like that, it certainly might make sense to use tables and to find reciprocals. Okay. Okay, so what I'd like you to do is a warm up. If you look at number 6, and again, you don't need to go into groups to do this, is use the table just to practice finding reciprocals. So find reciprocals for 16 and 40 and 50. And so you would just locate those numbers. There's 3 columns here. The first column, I'm just kind of explaining what it means. That wasn't part of the column. But use this table to find the reciprocals of 16, 40, and 50. I'll just give you a couple of minutes to work where you are. We won't go into groups. And the idea is just to get used to the table. If you have any questions, let me know. We can talk, or I can go over it. And we'll go over the answers together too.
So if I'm understanding this right, the 5th column is saying that 1 over 16 equals 0 semicolon 3 comma 45.
Yes.
Okay.
And does that, in terms of scale, does that make sense to you? That 1 over 16 would be about 3 over 20 plus change? I mean, 3 over 60 plus change?
Yeah, I think it makes sense.
Yeah. So you want to keep your mathematical intuition with that, but that's exactly how you read it. Okay, so I'll go through these. So we looked at 1 over 16. I see that 16 times 345 is equal to 60. So that means if I adjust things a little bit, I get that 1 over 16 would be equal to semicolon 345. And if you think about it, that's going to be 3 over 60 plus 45 over 60 squared. That's about 1/20th. Or that is exactly 1/20th. So you're adding something to 1/20th. That makes sense that it's going to be 1 over 16. So then for 1 over 40, I look down and I see that 1 over 40, I see 130 next to it. So that would be, oops, sorry, that should be 0 semicolon 1 comma 30 comma, and that would be 1 over 60 plus 30 over 60 squared. And again, that seems reasonable. That you 2 over 60 would be too big, so it would be 160 plus some change. And then for 50, I'd go to 50 and I see 1 comma 12. So 50 would be 0 semicolon 1 comma 12. And again, if you think about what that means in terms of fractions, 1 over 60th plus less change than above. Okay. 2 over 60 would obviously be too big, so it has to be 160 plus something over 60 squared. Okay. Okay, so questions about that? So if you look back to the questions, I'll break you into groups. You have these two things to set up. You know what the reciprocals are. And again, even though it's division, we're going to be multiplying 1 comma 33 times 1 over 50. So this is what we're doing. And then you can use the 1 over 30 table up here to do the computation. So again, I'm picking numbers that make it easy with that table. Okay, so I'm going to break you into groups and then we'll get to work. So I'll do 4 groups. That means most groups will be 3. You'll have 1 with 4. Okay, questions before we do the breakout groups? Okay, here we go.
Oh, hello, sir.
Hello, just seeing how you're doing.
All right.
Yeah, just I think we're all just working through them.
Yep.
Second nature now? Not
A
quite.
bit. It's taken a bit of refreshing, but yeah,
Yeah.
it's not bad.
Getting closer.
Yeah, getting closer, right? Converging. Okay.
Yep.
Okay, so just let me know. It should be cut and dry, but let me know if you have any questions.
All right.
Okay, or let me know too when you're done. Okay. Hello, just checking in to see how you're doing. See if you have any questions. Oops, sorry. I lost you for a second. That's okay. Everything going well? Okay. Okie doke. Let me know if you need any, let me know when you're done or if you have any questions. Okay, thanks. Just checking in. How you doing? Any questions?
Just grinding them out right now.
Cranking it out.
Yeah.
Getting to be second nature, right? Just like regular Babylonian base 60 multiplication. Yeah. Okay. Okay. So let me know if you have questions or when you're done. Okay. Hello, just here to see if you have any questions. See how you're doing.
Just working on number 6.
And you can start number 7 and think about how you'd approach that. I'll do that with the class. It's kind of a bizarre question. But, yeah.
Do you have the answer for number 6?
Let's see. I did it. I got an answer.
Okay, because I have
Maybe optimistic to say the answer. Okay.
I have 5 semicolon 48 comma 5. I think it's wrong though, and I'm trying to figure out why.
Well, I got the wrong answer too. Looking at my work, I had 30 in the last column, but I think it should have been a 15.
Mm-hmm.
Because I had 430 plus 1 plus 730 plus 1115.
I think we're supposed. Wait, I should have 45 in this last column. Wait, does this make it correct? This might make it correct.
I just want to make sure that I set it up right.
Oh, that made it work. Okay, cool. Well, I got it working. So
Okay, so what did you get?
5 semicolon 48 comma 45, and I've checked the answer using calculator because it all adds up correctly
Okay,
compared to 93 over
Okay.
16.
Okay, sounds good. I think I see where I made my mistake. No, wait. Okay. Okay.
Because I accidentally, because I had a semicolon 2 and I was reading it as semicolon 0 comma 2.
Uh-huh.
So it was moving stuff around how it shouldn't have been.
So other people, Paige, do you have any questions or?
No.
Good. Okay. Yep.
Mm-mm.
Okay, good. It's making sense how to set it up. Yeah. Molly, same thing?
Yeah, no, it makes sense.
Okay, good. So it should be second nature, almost second nature, right? Getting there. Yeah. Okay. So yeah. So if you want to try to, I'm going to do 7 for the class, but think about how you might do that. And, you know, one way to think about it is how you express 7 as a repeating, 1 over 7 is a repeating decimal. Base 10, how you get to that point, and then try to do that for base 60. So, okay. Okie doke, I am going to go out and see. I think people are doing pretty well, so I'm just let me know when you're done with number 6. Or you are, I guess you already are, right? Bryce says, yeah. The rest of you, yeah. Okay, good. Okay. I'll check the other groups. I'll probably call you back in a couple of minutes. Hey, I think everybody's out. Okay. So what did people get for number 5? How about the first group? So let's say you can just type it out.
So my group got 1 semicolon 51 comma 36.
Okay. How about the rest of you? If you got something different, okay, good. That's what I got. Okay, how about for the second? How about for number 6?
5 semicolon 48 comma 45.
Okay. How about other people?
I got the same thing.
Same thing? Okay, good. Okay, good. Okay. So yeah. So now you know how to do it like Babylonians. Like, you know, and it should make sense, you know, just imagine again, like I was talking about last week, if you had a whole bunch of tables, you could be doing these calculations. Just kind of, you know, not quite by rote, but like just, you know, really quickly. Okay. Okay. So I just want to sort of end this, and I'm going to look at, I know, let me get my paper centered. I want to look at 1/7. Here, I think that's easier than me moving. Okay, good. Okay. And then if we want to figure in base 10, this repeats. So the idea is you go 7 into 10, well, decimal, of course. That's 1. 7 into 30, 4, 28. Carry the 2. 7 into 20 goes 2, 14. 7 into 60 goes 8, 56. 7 into 40 goes 5 times. Carry the 5. 7 goes into 57 times. And then that's when I stop because I'm back. I get a repeat. I'm back to where I started. Okay. So how would you do this base 60? I'm going to just write that. But how do we need to think of that 1 when it's not big enough? So rather than having a 10 here, what would we have here? Remember, because here you multiply by 10. That's where we get the decimal point from 7 to 10, and then you subtract. So here, rather than 10, what are you multiplying by? 60, right? So you're going to go 7 into 60. Okay, well, so how many times does 7 go into 60? Well, 8. Then I have a remainder of 40. Sorry, of 4, but that becomes 40. So I'm really going to have to do this in my head or on a piece of paper to the side in reality. So I'm doing 7 into 240. Okay. And so I'm going to pretend I'm not doing it in base 10, but I am. So I see that what I get is I'm going to get a 34. But I get to 230, I'm too short. So I get to 238 here. So remember, 238 is too short of 40, so it's 3 comma 58, sorry. Then I do a 20 here, which is actually 120. So again, I have to go 7 into 120. I get 17, but my remainder is going to be 1. So 7 times 17 is 119, so 159. And then I get a 1 here, and that's what I started with. So what this would be to a Babylonian would be something like this. And I think there's a table where they carry it out, not just 834.17, but they carry it out further. Now we think of this number here as repeating, because it's going to cycle back with period 6. Here, this would be repeating, but again, without a real concept of infinity, the speculation is that there's no record that they saw this as infinitely repeating. But what they did is, depending on the accuracy they needed for a computation, is they would use maybe a cycle of 6 or 9 or something like that. So they would have some sense of how accurate they needed it. And if they wanted something really accurate, they would repeat. So they, rather than use 834.17 for 1/7 or dividing by 7, they might use 834.17, 834.17. Okay. So again, we get the same concept. 7 and 60 have no common factors. So it becomes an infinitely repeating sexagesimal, just like 7 and 10 have no common factors. So 1/7 is repeating. So there are numbers that you would repeat, and 1/7 in base 60 would be the first one that doesn't terminate, because it's the first number that doesn't have a factor in common with 60. 8, 9, 10 do, then 11 doesn't, 13 doesn't, and so forth. Okay. And
I have
so,
a question.
sure.
How did they handle rounding? Was it similar to how you do it in base 10?
I don't know. My guess is that they would do it the same way. I haven't seen enough of that, those really detailed computations. The one I've seen involving this doesn't round. I mean, that would, the next digit's 8, so that wouldn't round. But I would imagine they would do something similar to what we did. It seems like an intuitive kind of thing. Okay. But that's a good question. Okay. Okie doke. So again, that's just wanted to go over that. So now you should be able to have some facility for computing in base 60, understanding how it works. It's different and it requires thought. And for me, it requires doing base 10 things off to the side. Just because I don't do it enough. Okay. So any questions about that, about these tables or anything before we move on? So handout 7, I had a picture of it in this tablet in the lecture, in the online video, I believe. And again, it's not a very big tablet, but this is the tablet translated, to modern numeration. And, it's a strange thing. It would take if you just found this as a relic, like an archaeologist, and you wonder what this is, you'd give it to somebody that understood the mathematics of the time. And there's a famous person, Otto, I'm blanking on his last name. I think it's Neugebharten, and he wrote a book in the 20s or 30s about the mathematics of ancient Babylon. So he knew, he was able to read the original sources. So you would give this to somebody, and it would be like, what is this? So what does this table represent? And this is the closest clue right here. And so let's look at it in base 10. So you have the base 10 version below. And so I'm looking at the line, the 11th line. So 45 and 75. And I don't know if that's enough of a clue to think about what it is. And again, it would take some detective work. And when you look at these things, you think about it for a long time, sometimes days. Well, the missing number here is 60. So you have this thing right here, 45, 60, 75. And can anybody see what that represents? Oh, I think my page is frozen. This feed is over here, so let me try something else. I'm going to use the I'm not frozen, right? Me speaking. Okay, but this is definitely, this camera froze, so let me use the whiteboard. So I'm looking to, and then I'll unfreeze it in a bit. So I'm looking for the 11th row, and I see the number 45 and 75. And then I'm adding the number 50. And if I divide each of these by 15, I get 3 times 15. Sorry, add the number 60, not 50. 4 times 15, and then 5 times 15. And that's a 4, not a plus. I'm going to circle these numbers, 3, 4, and 5. Do those numbers ring a bell? How they might relate?
Is it a Pythagorean
Pythagorean
triple?
Exactly. Okay. And so think of, just hold that thought for a second. And so I just need to do something in my head really quickly. Okay, so what I want you to do next is to do 75 squared, just over 60 squared. Again, this is random, but I'll make sense of it in a second. So we think we got triples. So I want you to look at that number and see what you get. I'll do the same thing. I'll just get out my browser because I'm lazy. So I get 15625. And do you find that anywhere on the table?
It's with X 45 and D 75.
Okay, exactly. Or if I'm seeing it, I'm looking at the base 10 table, and I see it in the left-hand column of the base 10 table.
Mm-hmm.
Right. So let's draw the triangle. I'll put the 4 side here, put the 3 side here, and the 5. It's a 3, 4, 5. I can put the bigger numbers, but you know, actually, I might as well do what they have, just so it works out. And I'm going to put this here, my angle theta. So what does the ratio 75 over 60 represent? It's opposite, it's hypotenuse over opposite. But squared. So what trig ratio is that? Remember, it's the inverse of the cosine. Cosine is opposite over adjacent. So it's going to be cosecant quantity squared. Okay. Or if you reverse the angles up here and you think of this angle, it would be the secant square root of phi. And I think that's how people usually do it. Okay. Okay. So then, just again, imagine this is the, you're looking at this and you've said 70, you got the insight, okay, this is a 3, 4, 5. And then you say, I wonder what that number at the left means. Then after a few hours more of thinking about it and trying things, you stumble upon that this is this ratio right here. And, so depending on how you view it, it's either a cosecant or a secant squared. And then you go back and you do the same thing for other entries. You find the missing entry and you see that that first column is always going to be, if this is our y, and this is the x, I just want to use consistent notation, and this is d, then that first column is always going to be the side you're not giving the hypotenuse, the big square, the big number in the triplet over the second biggest number, quantity squared. And you can check that out, and it works out perfectly. And you can see here how far they worked out some of those numbers. I put ... down there just because I truncated many of them. But you can see they worked them out to 1, 2, 3, 4, 5, 6 sexagesimal places. If you look at like the fourth entry. If you look at the second entry, 1, 2, 3, 4, 5, 6, 7 places. They did some pretty massive calculations they're doing. And you just want to think about how they do those. They're finding reciprocals of really big numbers. So it's really, it's pretty impressive. Considering what we've done so far, imagine doing some of these calculations with much bigger numbers. And we assume there were tables that allowed them to do this. So this is really, if you think about, just step back and think about it. Let's, again, what the table is. I'm going to see if I'm still frozen, if my camera still is. I'm going to stop the share. Yeah, it looks like it is, which is fine. So, because you can look at it. So, I have the top table in sexagesimal. I have it in decimal so we can understand it better. And, we've cracked the code that we have 2 members of a triple. The third isn't on there. If you look at the tablet, it's cracked. So maybe that was on there. And notice how it mentions, this is a horrible translation. I wouldn't know how to translate it better, but because I don't know the original language. But the holding square of the diagonal from which one is torn so that the short side comes up. So it's like you're taking a triangle with you're taking a rectangle. You're taking the diagonal. So let me show you what I mean. Again, I can't use my document camera. So let me just clear all this. Here's my square, or my rectangle, sorry. The table gives the short side. You put a diagonal in there, that's your D. And this is the missing side. That's going to be a right triangle. So again, it's tortured language, but the holding square of the diagonal from which one is torn, so the short side comes out. So you imagine that you're taking this square, the way I kind of translate that and think of it, and you're just thinking of it like that. So you're tearing out part of it, and then this is the missing entry. You have the short side in there. Okay. So we got this table of triples, and the first column is going to be the secant ratio or the cosecant ratio, whichever way you want to think about it. It's the ratio of the square of the diagonal to the square of the missing side, and they list them in order. And the angles are approaching 45 degrees and approaching 30 degrees. if we want to think of them those ways. So I'm trying to think what to say next. I don't want to say too much yet, but so I just want to make sure that you understand what that is. That it's a listing of triples missing the longest, the longest non-hypotenuse side, and it's arranged by the ratios of the squares. Okay. Weird, right? And huge, if you look at the base 60 stuff, that's some pretty serious calculations. And I have read, though I haven't gone and verified it myself, that there's only like one triple that's missing, and by that they mean that from the top number 159 to the bottom, there's only one triple that's reasonably sized, whose ratio is reasonably sized, that's not on there. So it's a very comprehensive list. And so this is just, it's a table of triples with the ratio, and they're organized by the ratio. So what was it used for? What might it have been used for? Just sort of spitballing and, talking without thinking. Your guess is as good as mine. I mean, I don't know if anybody has any thoughts about what it might have been used for. Okay, I'm going to imagine that I'm a teacher in ancient Mesopotamia, and I want to give you a problem. And my problems are going to be, here's two parts of a triple, find the missing triple, find the missing element. So I could use this table as a way to generate those problems. That's one suggestion as a teaching device. Another suggestion is that somebody wanted to, this is what mathematicians do today, and they've done it, obviously before today, is that mathematicians want to classify and organize the mathematical information. So maybe this is a way of, maybe this is a part of a much larger program, and this is organizing all triples of reasonable sizes whose ratios are between 2 and 1/3 and 1 1/3. Something along that line. So maybe it's part of just somebody wanted to organize all the triples in some sort of fashion. So it's a mathematical thing. And that, I mean pure mathematical, not for teaching, but just something that somebody wanted to do to organize the information. So again, we don't know what it was for. However, I've never read anybody that says that this is trigonometry in the sense we think about it, using this for angle measurement. I mean, it's certainly trigonometry in the sense they're using what we would recognize as a trigonometric ratio, but it's number theory. That's sort of the prevailing opinion, that this is number theory. Advanced number theory is about the study of whole numbers and their properties and the different ways they interrelate. Triples are a big part of that. This is giving you all the triples in a certain range. Okay, so that's one of the thoughts. Okay, so just getting you thinking about this. Do you have any questions about it? Are you able to see? I mean, are you able to sort of like, okay, I understand what this is. I understand what's on there.
I think so. Yeah.
Okay. Yeah. Yeah. And then again, and just be appreciative of the word of that labor that it took to decipher all this and figure all this out. Okay. I have an obvious question about this, and I don't know if you have the same question. Do you have any curiosities about this table? Like, there's one to me that's driving me crazy. And have you seen the viral video of the woman who's doing her makeup talking about whether math is real or not? Sort of gotten a lot of attention.
Let's watch it.
We will, don't worry. We're definitely going to watch it. Not today, but definitely at some point when we talk about the Greeks, because she mentions Pythagoras. It's kind of an interesting pop cultural artifact of mathematics. But her question, she goes, is math real? How did people think of this stuff? So that's my question, is how did people find these numbers? I mean, thinking about it makes sense. You want to organize all the triples, but how did they figure out these triples? If I asked you to figure out, you know, give me some 5-digit triples that aren't obvious, that aren't 3, 4, 5s or 5, 12, 13s, you know, you'd have to think about that. So again, that's one of the questions. Where did this come from? And so what I want to do next is I want to go through an algorithm that generates triples. And we may end up working on this on Thursday. I don't want to rush it. I want to make sure we understand it. Okay. And I'm going to hopefully try to see if I can unfreeze my phone, because I definitely want to use. Good, I think we're good again. And the reason my phone froze is because I let it go to sleep. I just realized that when I looked at it. Okay. So on the back of this handout, I have a more complete reciprocal table. You know, it doesn't have numbers with a factor that's not, it doesn't have like 1,7, 111, 113 or 14, because 14 is going to be related to 1,7. So it's missing those. But it has all the other ones that are commensurate with 60, so the chair factors with 60. So this is one of the keys to it here. And so here's an algorithm that I'm explaining here, and I'm going to walk through it. And I have a website that it's on the front, which I think is really an interesting website. It's the one that's at David Joyce, so the first one. So it's an algorithm that he has. It's similar to one that's in the book by Victor Katz that some people used. And I find that version a little bit too convoluted. And I came up with this version on my own, but then I found that, of course, it's on other websites as well. And to me, this version is a little bit simplified from the one in that text. And I think it's closer. I think it bears similarities with the the quadratic in a way. So I'm going to go through that. And again, we may just go through the algorithm once and not with an example. But so the first step is that you choose reciprocals A and B. And the reciprocals I'm going to choose are going to be 6 over 5 and 5 over 6. And to get 6, 5, I multiply 6 times 1/5. And so I just look in the table and find the algorithm there. And again, I'm not going to worry about it. And then to find 5, 6, I would multiply 5 times 1/6, again, using the reciprocal table, like what we did earlier. I'm going to keep it in base 10. But those are the numbers that I have in mind, 5, 6, and 6, 5. And then A is always going to be the reciprocal that's greater than 1, and B is going to be the reciprocal that's less than 1. Okay. And so we always have A times B is equal to 1 because they're reciprocals. Okay. So this is going to seem weird, but maybe not so weird. So we're going to introduce new variables V and U. And A is going to be V plus U, and then B is going to be V minus U. And well, that's weird. But I just want to point out a couple of things. If I multiply AB, I have 1 equaling A, which is V plus U, B, which is V minus U. I get a difference of squares. Now, for reasons which will be made clear later, I hope, I'm going to think of this as a fraction d over y squared, and this is a fraction x over y squared. And what happens if I clear fractions? If I multiply everything by y squared, notice I get triples. So I have 1 equaling this. I multiply by y squared, and I get y squared equals d squared minus x squared plus y squared is equal to d squared. So you can think of this as an algebraic trick to generate triples. And again, somebody had to think this up, and it's clever. But I'm going to look a little bit more closely here about what A and B are. If I add A plus B, what do I get in terms of V and U? What cancels?
U.
Right. So I get 2V. So V is going to be the average of A plus B. And where have you seen averages before?
Midpoint.
Yeah, when we were doing the quadratic. Remember that the one of those methods worked. You found the average of the length plus the width, and then you found the average and you found out what you needed to subtract and add. So to me, it's reminiscent of that. And then what if I subtract A minus B? What do I get? Sorry. Didn't do that right. No wonder you're silent. V plus U minus quantity, V minus U. V plus U minus V plus U. 2U. So U is equal to the difference divided by 2. And again, you saw something similar in the quadratic length width algorithm that two of you talked about. Okay. So again, I'm going to go through it, but those are the key ideas. So here's what we do. Start with the reciprocal pair. AB is equal to 1, and A is going to be the bigger of the two. And these are always positive. Then I set A is equal to V plus U. B is equal to V minus U. Okay. And then what I notice is that I get 1 equal to AB, V plus U, V minus U, which we saw was V squared minus U squared. And so that's, I'm going through, so, and then so this is the first step, this is the second step. And the third step I just pointed out, which we already did, we saw that V is equal to the average of A plus B, U is equal to the average of the difference. We already saw that. And then we're going to set V equal to D over Y. And then U, we're going to set that equal to X over Y. And then I'm going to substitute them back into number 2. So that's what I get in the fourth step. I get 1 equals V squared minus U squared equals V squared and then I clear the fractions as we did above. I multiplied both sides by y squared. I get y squared equals d squared minus x squared. And then that yields my triple. And what I want to do is I want to go through this with 6/5 and 5/6. But in terms of the algorithm, does that make sense? Okay. Again, the one I really think that the one that's in the text, which we're not using it, I used to use it as a text. It's a good book, and I can copy this part of it if people would like. But it's more convoluted, and to me, this seems more in keeping with the kind of thing that they did with, the length width problems. It's the same kind of thinking, but applied in a slightly different context. This is not a solution to the quadratic, but to me, it's the same kind of thinking. And when I was looking at Kat's once, I was thinking of that the version he gave seemed too convoluted, and it just seemed maybe that's all they did. And to me, I think this makes more sense to me. And again, it's on David Joyce's website. So let's do that A is equal to 6/5 and B is 5/6. So we'll go through the second step. We set 6/5 equal to V plus U, and 5/6 is equal to V minus U. And then that means V is going to be equal to 6/5 plus 5/6 over 2. So the average of the sum. And U is going to be equal to 6/5 minus 5/6 over 2. And notice if I turn this into a common denominator, I multiply this side by 6 over 6, this times 5 over 5. 36 plus 25 is 61. I get 30 here, but it's 30 over 2, so that's going to be 60. That's what V is. That's D over Y. And then I do the same thing over here. I'm going to get 36 over 30 minus 25 over 30 divided by 2. That's going to be 11 over 60, and that's going to be X over Y. So now I go back to step 4. 1 is equal to 61 60th squared, V squared, minus U squared, minus 11 over 60 squared. Multiply through by 60 squared. 60 squared is equal to 61 squared minus 11 squared. 11 squared plus 60 squared is equal to 61 squared. Okay. Sorry, it's off the page. Okay. Again, did everybody follow that? Any questions about that? Could you, I assume you could, with time, you could go through that and figure it out for your, go through it yourself. So look at this number. I'm curious, is this on the table? So let's compute this. 61 squared over 60 squared. And tell me what you get. This is what I got. I'm just going to go to a couple of places, round to 3. Okay. Now, why is that not on the table?
Because their fractions are their
Yeah.
decimals are descending, and this is
Yeah.
a lot smaller than any of them.
Yeah, maybe it's on another table. maybe this, maybe it's on page 2 of this table or page 3 or something like that. Okay. So I'll let you, we'll talk more about this maybe a little bit on Thursday, but this is from what I've read, this is speculation. There's no proof that this is the algorithm that they used. People would put up the answer would be, why is this reasonable speculation? Well, because they knew about reciprocals. We saw the reciprocal tables, so those were important to them. None of these steps are very hard. I mean, they're clever and they're creative, but we're not talking about calculus or abstract algebra. It's computational. They did these kinds of things before. There's some evidence of difference of squares, but clearly taking these averages is something we saw in the length width problem. So again, it's familiar mathematics. And then we can go through this with other reciprocals and we can generate elements on this table. So, so again, this isn't proof of what they did, but it's a reasonable speculation of what they of what they did. And I hope that, so when you argue historically, you can make stuff up, and BS, but usually what you're going to have to be able to do if you want people to listen to you is to say, well, this makes sense. It's consistent with what we know about the history. So it's possible, and come up with a better explanation if you don't think this is what they did, So anyway, so that's kind of what I was doing here with this explanation. And then, so any questions about that? I have one more point to make and maybe just a couple of closing remarks, and it's a short point. But I want to see if there's any questions about that first. Okay. So one question I have is, notice this is d over y and x over y, and that seems arbitrary. How do we know we're going to get the same denominator for both of these? Because that's quite a jump. What we're saying is that no matter what reciprocals I pick, when I divide by 2, I'm going to get a common denominator between a plus b over 2 and a minus b over 2. And notice what we did here. That's kind of my clue, is that something like this is always going to happen. We got a common denominator of 60. So something about the way that you combine these is why you get the common denominator. I mean, I'm saying something about it, and I'm not trying to, I want you to think about it. Okay, so that's pretty much what I have today. I will talk a little bit about this on the 3rd page. Okay, just 1 minute. Okay. I have somebody from the census is at my door, but just look at the 3rd page over here, and there's just some questions on these, just comments, questions about the sheet. So we may talk about some of these on Thursday. So that's all I have. I'm going to go talk to the census person in a second, but if you have, I think it'll just be quick, but if you have a question, I'll be right back because I've already filled in my census. Okay. If you don't have a question, you're free to go since it's 6:15, but I'll be right back if you have questions. Hi. Yeah. Thank you. I appreciate it.